So hello and welcome back. Today we will have lecture 9-2 on balanced three-phase systems and sources and analysis of Wye-Wye circuits. You should be reading sections 11.1 through 11.3 of your textbook in order to follow along with this lecture. This content will be on the final exam. This is the final topic in this course, which is three-phase systems. The learning objectives for today's lecture are to be able to briefly define and explain balanced three-phase voltages and briefly define and explain Wye and Delta connected sources.
We have a circuit here, and I'm only showing one of them, but assume that this is one phase of a Wye-Wye system, right? If it's one phase of a Wye-Wye system, I want to take this balanced three-phase system with a positive sequence that has an impedance of 0.2 plus J 0.5 ohms per phase. So here's my line impedance. This is what that is. And an internal voltage of 120 volts per phase. That's what this is showing here. And the generator feeds a balanced three-phase Y-connected load. So remember, this is a Wye-Wye system. So it's Y on both sides, but this is only phase A shown here. And that has an impedance of 39 plus J 28 ohms. And the line impedance for this side is 0.8 plus J 1.5 ohms. Your first step is to calculate the line current. At that point, you're just analyzing this circuit like you would any other circuit. It's just a matter of what do we do with that information once we get it. So without my help, I want you guys to find the current in that loop. This is the same thing you've been doing all along. Find the current in that loop. Okay, it looks like you did some rounding there, Alfred. So the line current, IAA, is 120 with an angle of 0 degrees, divided by 0.2 plus J 0.5 plus 0.8 plus J 1.5 plus 39 plus J 28. So I took the voltage and divided it by all those impedances. I got 2.4 with an angle of negative 36.87 degrees. Is anybody there? Okay. Since it said positive sequence, I can then find IBB and I can find ICC. Positive sequence means I delay B by 120 next. So that's 2.4 with an angle of negative 36.87 minus 120 degrees. So IBB is 2.4 with an angle of negative 156.87 degrees. I delayed it by 120 degrees. Is everybody with me so far? Okay. ICC is when I delay IBB by 120 degrees. 120, sorry, I can't talk. 120 degrees. So this would be IBB delayed by 120 degrees. So that ends up being 2.4 with an angle of negative 276.87. I can't talk. Negative 276.87 degrees. Or it might make more sense to just write that as the positive value, which is 83.13 degrees. Just like this one was the same as IAA delayed by 120. All right, so this was the line current. This is called the line currents. For a Y-connected system, line currents equal phase currents. So that means these are also your phase currents. So that means the answers for Part B are that IAN equals IAA, IBN equals IBB, and ICN equals ICC. Okay? Phase currents equal line currents for Wye-Wye connected. So A and B is done. B is asking for voltages. I was giving you line currents and phase. So this is that. So that's okay. This is done. Does it not ask for phase currents anywhere? I guess it doesn't. All right. So here are your phase currents. You're right. So now the voltages, the relationship is first find VAN. Phase voltage at the load, find VAN. How can I find VAN? Do I know the current? Do I know the impedance? Find VAN. The good news is you only have to do it once because then you just delay the angle. So that's going to be IAA times 39 plus J28. IAA equals 39, IAA times 39 plus J28. So VAN equals 115.22 with an angle of negative 1.919 degrees. And now for VBN, delay VAN by 120 degrees. For VCN, delay VBN by 120 degrees. Very good. VCN is 115.22 with an angle of negative 241.19 degrees. Or you can write it with the positive angle. Okay? Any questions so far? So this one with the positive angle is 115.22 with an angle of positive 118.81 degrees. So VCN with the positive angle is 115.22 with an angle of 118.81 degrees. So what we're going to do next is find our line voltages, which is part E. And the relationship between the line voltages and the phase voltages is that the line voltages are equal to square root of 3 times the phase voltages. That's magnitude, right? And for the angle for the line voltages, that is the angle for the phase voltage plus 30 degrees. Or you could write this all as one, as V line equals V square root of 3, V phase, adding on an angle of 30 degrees. Okay, so that's what you're going to do. The first thing you want to find is V AB, and that's going to be square root of 3 VAN angle 30 degrees. Find VAB. And then once you find the first one, you just use 120 to find the rest of them. So find VAB, and then use VAB to find VBC and VCA. Just shift by 120. So this is square root of 3, angle 30 degrees, times VAN, which was 115.22 with an angle of negative 1.19 degrees. What is VAB? I think I missed some impedances, but you get the point. But something like this. So when it's asking you things about the line voltages, it's saying that AB at the load would be right here. It's the voltage across line A and line B. Or BC would be right there. So you can't actually see it on that circuit, but remember, this is one phase of a three-phase system. It's just once we get the values for one phase, I can use that to get the other two phases. Other questions? Okay, so VAB. VAB ends up being 199.58 with an angle of 28.81 degrees. Did anyone get that? Okay, Ethan says yes. BBC is also 199.58 with an angle of negative 91.19 degrees. Remember, once you find the first one, you just delay by 120 to get the next two. So just subtract 120 from the angle to get that one, subtract 120 from the angle to get this one. So this one is 199.58 with an angle of negative 211.19 degrees. Okay, so this ends up being VAB delayed by 120 degrees. And this ends up being BBC delayed by 120 degrees. So next we're going to find the source line voltage. So this will be part D, the source line voltage. Part D is going to be the source line voltage. So Alfred, looking at that question you asked me earlier, source line voltage is going to be V lowercase ab, and that would be right there. V lowercase ab. So V lowercase ab is going to equal the square root of 3, angle 30 degrees. So it's going to be that times VAN. V lowercase ab equals the square root of 3, the angle of 30 degrees, VAN. And actually, we got to find VAN because that impedance is counted as part of VAN. So hold on, VAN is actually going to be on the other side here. So if this is 0.2 ohms and J 0.5 ohms, VAB is actually on the other side here. It's after the impedance. So let's talk about how we find VAN. VAN is now going to not just be this voltage value, but that voltage value minus the drop across its internal impedance. So if this is 120 angle 0 degrees, then VAN is going to be 120 angle 0 degrees minus 0.2 plus J 0.5 times the line current to get the voltage after the impedance. So that would be VAN, and VAN is the voltage from here to the neutral. From there to the neutral would be VAN, the voltage after the source, and after the voltage drop for the internal impedance. VAN would be from that node to the neutral, and VAB would be from that node to the B line after the impedance. The current we found last week is 2.4 with an angle of negative 36.87 degrees. So I'm going to take the voltage source minus the impedance times 2.4 with an angle of negative 36.87 degrees. So VAN is 118.9. With an angle of negative 0.32 degrees. Okay, so then once again, I delay it by 120 degrees to get VBN and VCN. I delay by 120 to get VBN and VCN. Miguel, you have a question? What's VBN? What's VBN? And actually, I reversed these. A and B and C and is actually D. This is part D of the question, and this is part E of the question. Okay. So you're going to delay them by 120. So this is 118.9 with an angle of negative 120.32 degrees. And this one is also 118.9 with an angle of negative 240.32 degrees. So then VAB is the square root of 3 times 118.9, and you add 30 degrees to the angle of negative 0.32. So VAB is 205.94 with an angle of 29.68 degrees. You take VAN, multiply the magnitude by the square root of 3, and add 30 degrees to the angle. And you could keep doing that, or you can just delay that one to find BC and CA. So VBC is the same magnitude, but you delay by 120 degrees. Same magnitude, but you delay by 120 degrees. So this one is negative 90.32 degrees. And then VCA is same magnitude, and you delay it by 120 degrees again. So that's negative 210.32 degrees. So let's review what we did here. We took a Wye-Wye system, found one phase of the system, found the voltages and currents, line voltages and phase voltages, and line currents and phase currents, and then used those with our formula to get all the voltages and currents for the three-phase system. So if you can rewrite any system as a Wye-Wye, you can then do a KVL loop to get the other values. So even if you have a Wye-Delta, Delta Y, whatever, the easiest thing to do is change it to a Wye-Wye and get the values you need.